Hey, everybody. First of all, it's been about 4 years since I've been able to come to Computex. There was the whole COVID thing, which was a real bummer. And then there was a couple years where I was switching from one place to another. Well, and if you know me, I'm really excited to be here. I joined Intel because I really believe in the roadmap. The roadmap is king for me. I'm in technical marketing. I deal with the latest silicon all day long. And being confident in the architectures and the performance and the power is what I'm passionate about as an individual human being. So what I'm going to go through today is kind of the highlight reel of what makes Lunar Lake so good, so impressive to me technically. And then, of course, if you have specific questions about, hey, what's this little buffer here or this little cache here in the core or the graphics, there are sessions. They run multiple times per day, and you'll be able to dig into those. So let's dive right into Lunar Lake. You saw this today, but I just want to briefly touch on this. You know, it is not about the instruction set. It is not x86. It is not ARM that determines power. It is the physical design of the chip. It is the floor plan of the chip. It is the process technology used. It is the packaging technology used. It is relentlessly optimizing every component in that platform. 1-watt panels, the most efficient memory, the most efficient SSDs. That is what drives battery life. That is what drives CPU power. So what you will see from Lunar Lake is x86 power like you have never seen it before. Okay? We relentlessly tackled every single execution engine in this chip to extract the most performance per watt that we could. We touched everything: graphics, NPU, packaging, cores, fabric. Every component received an improvement. Okay? Core performance is key, right? We talk a lot about AI PC, but fundamental computing must come first. I am a PC enthusiast. I care about the core. I care about graphics. AI is an and for me. In a few years, there will be a time where AI is completely seamless, infused in everything that you are doing on your PC. And that's the same trajectory graphics had many years ago. I used to be in hardware reviews, and there was a time when these graphics chips came into the CPUs, and we all thought, what is this thing doing here? You can't even play a game on it. Why do we have graphics in a CPU? Now today, it runs your web browser. It runs Microsoft Office, your web page rendering, Discord is composited by GPU hardware, and AI will get there too. But it all comes back to fundamentals. It is the CPU and the graphics performance that kind of underpins everything that you touch. Right? So core performance was a key focus area. And then finally, graphics and AI, your vector and matrix math, huge improvements in this category. And we'll touch on all of these in a little more detail. So you saw the Lunar Lake construction, and I now have the privilege of diving a little bit deeper into what that means. So we have a base tile, right? It's a passive base tile based on Intel 1227 process technology. And then you have the compute tile, which is on TSMC N3B. And then you have the platform controller tile. You could call that your chipset if you wanted to. That's on TSMC N6. And all of those tiles sit on that passive base layer interposer, and then that is mounted to the CPU package, where it also has direct access to the memory on the package. Memory on the package is a key innovation. Right? It allows us to reduce the footprint of the motherboard that the CPU sits on. By getting those chips off the board, you're not directly mounting LPDDR to the board. You can shrink the board correspondingly, make the number of layers in that motherboard thinner, which reduces complexity, reduces cost of the motherboard, so on and so forth. So memory on package is a key way we're extracting power. I'm going to say the word power a lot today. You can write down check marks every time I say it, but this is key. Memory on package is a great way to reduce power consumption in the system. Remember, it's not about the ISA, not about ARM, it's not about x86. It is about platform-level innovations that drive this power down. So if you can move memory off the motherboard onto the CPU package, you no longer need memory controllers with high power PHYs or links to off-chip memory. Right? That signaling to off-chip memory is expensive electrically. So moving memory on package is a great way to alleviate power consumption in the system. And so that 250 millimeters squared of area, we talked about that during the Q&A and the keynote, that is board space saved, and it runs up to 8533. Okay? So now we're going to dig into the architectural overview, cores, graphics, NPU, the meat and potatoes. We'll start with the performance cores. We touched on this just a little in the keynote, but one thing I want to leave you with is that the P-core is designed to be wider and extract higher instructions per cycle because the frequency comes down slightly, right? And we also removed hyperthreading, which I understand is a very bold thing for me to say, but there's some really good reasons for that. Hyperthreading necessitates a duplication of many architectural elements, particularly in the execution pipeline or tracking the state of a process. If you're trying to fill this pipeline with multiple threads, you need hardware to track that execution into the pipeline. That takes area, that takes power, and frankly, our E-cores are getting so good that we can deliver better than SMT or better than hyperthreading performance without hyperthreading. Right? So that is the key motivation for making the P-core wider and extracting more performance out of every megahertz. We also introduced fine-grained clock control, which is another power management innovation. If you can more precisely target the frequency you are trying to hit, you can better control the voltage or the power that the chip is consuming. So we now can choose intervals of clock selection at 16.6-ish megahertz, right? And if you've ever looked at the formula, the mathematical formula for power consumption, frequency plays an outsized role in that mathematical formula. So not overshooting your frequency target with a larger interval, that's beneficial for power. We also split vector or floating point and integer into separate pipes. Floating point is playing an increasingly big role, or you could call it vector, because that's AI. 30% of the software developers that Intel talks to, hundreds of software developers who are working on AI workloads, 30% of them are going to put their AI workloads on CPU because the CPU is king for latency. Many of the AI workloads will use the latency of the CPU, incredibly low, most responsive engine in the device, to deliver a really fast and responsive AI experience. So you'll see content if you go to the P-core session and the E-core session about us bolstering the size of our VNNI instructions and our AVX256 capability. And that is to drive that performance up in AI. The AI-based power management also introduces machine learning. We can actually analyze in real time what this workload is doing. Is it single thread, somewhat lightweight in intensity? Is it a very heavy single thread? Is it multi-thread but somewhat empty? We've all seen these workloads. You just open the Windows Task Manager and you've seen them in action, but the CPU can recognize what is going on and make the right decisions with Thread Director to make sure we land on the right core and are making the right frequency decisions, so on and so forth. But the key takeaway here is that the P-core is architected to be wider, put more down the pipe at one time, extract more performance. So from an IPC point of view, gen on gen, we're getting about 14% more performance at the same frequency out of our P-core. But that is only part of the story because a P-core must, by design, address a wide range of capabilities, a wide range of TDPs, a wide range of frequencies. And in some sections of that curve, we're nearly 20% improved. Right? So this means that the P-core can not only put more down the pipe, it is also much more flexible at scaling across multiple TDPs and power envelopes, which effectively increases the dynamic range of what these P-cores can do. And that's important as they take on interesting new workloads like AI, other computationally intense workloads. More multi-threading is always going to happen, or I should say more compute capability is always going to happen. So this is a really important innovation for us. The E-core is frankly, I think, the real star of the show. It's even more impressive than the P-core. The goal here is to, first and foremost, I talked about doubling vector. This is VNNI. This is your AI processing capability. But the other big thing, if I'll go to the next slide right away, we also made this core much, much wider. We also increased the cache size, deeper queues, and so we can simply put more through these cores. We also added more of them, which I'll touch on in a moment. Let me just jump right to the punchline. We're getting 68% more IPC out of this core. This is a floating point statement, right? So 68% versus our previous generation Meteor Lake. That is an absolutely astonishing gen-on-gen improvement in the throughput of the core. But you can see from the diagram on the right that if you look at multi-thread capability, we are significantly ahead, not only because we went from 2 cores to 4 in a low-power island context, but because these cores are so much faster than the previous generation. So one of the questions this morning is, hey, last gen you had 2 low-power E-cores, and then there were 4 E-cores, and now there's only 1 block of 4. That's true, because these cores scale way down low, where the low-power island did in Meteor Lake, right? So we cover that use case. And we've also doubled the core count versus last year's low-power island. So now we can get the E-core benefit too. And as you scale up in performance, we get a lot more out of all of these cores computationally. So that allows us to simplify the design, reduce the area of the die, and essentially collapse 2 features into one because these are simply more capable. So if we look at them together, one thing I'd want to highlight here is that these cores are designed, you saw this diagram this morning, I'll touch on it very briefly. You saw this morning because these cores are designed to cover a full range. We do what I call bottom-up scheduling, so E-core is first in scheduling. We want workloads to go to the most efficient core first, and then when the workload is too significant for that 4-core cluster to handle, only then do we move it upwards into the P-core. But remember, we do have Thread Director, we have intelligent scheduling technology, so yes, it is absolutely possible to jump straight to the P-core first. At the low end, the E-cores are actually somewhere between 20 and 80% more performant than the P-core. And at the high end, kind of the opposite's true. You get 50+% more performance out of the P-core versus the E-core, right? So this range is why we do P-cores and E-cores. This range is why you can remove technologies like SMT, which have been around for forever, because now we have core technologies that can bring that single thread and multi-thread performance that was previously only deliverable through a technology like hyperthreading. Okay, so we just get so much more out of these cores. So Thread Director is part and parcel of this technology. Thread Director has been around since the start of the hybrid era. If you are just coming up to speed on this technology, it is a combination silicon, firmware, and OS engine that allows us to decide with hints from the scheduler, with hints from the system firmware, where these threads should go. Right? Does it belong on the E-core? Does it belong on the P-core? And most importantly, why? What is the best decision for the platform? Thread Director makes that happen. There are a couple changes in this generation that are important to understand, and the first is in the lower left. We have new, what we call containment zones that can kind of influence where these workloads stay. And this is part of our machine learning algorithm that underpins Thread Director. We can see that a workload does not need P-cores. That is a real-time decision, right? You can assess the intensity of that thread, the utilization of the transistors, and go, this doesn't need P-cores. So we're going to constrain it to the efficiency zone. And the impact of this, when you give those knobs and dials to the operating system, to the user, to the firmware, is you have a wide range of system tuning capabilities available to extract the most power or the most performance or the most battery life out of the system. So P-core and E-core, they work because Thread Director makes that possible. This is a dynamic policy, and so I mentioned bottoms up. By dynamic, it means I can start with the P-core if I want to. I can start with the E-core if I want to, but our default mode, unzoned mode, is starting with the E-cores. So we start with the E-cores because they're hugely performant, much more performant. We talked about that, somewhere between 60% and 4x the previous generation, depending on where you are. And we'll go the E-core first, a single core, and then we can expand outwards to consume multiple E-cores, and then if we need to, we will evict upwards into the P-core complex. So it all depends on that real-time analysis of the workload to decide where these threads go. One interesting tidbit is Microsoft Teams, which I basically live on. This is actually quite intense from a power management point of view. You would not think that, but Microsoft Teams is multiple real-time video streams. It is now taking on AI acceleration for improving background blurring and artificial backdrops, image enhancement, quality correction. So there's actually a lot in the silicon that's lit up when you do something seemingly so simple as teleconferencing. Because of this low power island improvement, or this E-core cluster improvement, we're able to drive power down, real measured active power, by 35%. Many workloads in Windows land are like Teams. Seemingly simple, seemingly straightforward, but they actually have, from a power management point of view, pretty complex requirements. And if you don't control those threads by technologies like Thread Director, which works in concert with the Windows scheduler, you do not get all the power efficiency that you are entitled to. And that can shave hours off of your battery life experience. And obviously, that's not great. Nobody wants that. So Teams is an interesting one. And just as an example, this is a live trace of Microsoft Office. And this might be word processing or light PowerPoint, but we start on the E-cores, right? We start there, and when the workload gets more intense, when we start firing up more threads, then this live trace clearly demonstrates we're shifting to the P-core instead. And so if you have access to an application profiler, which there are many available in Windows land, you will be able to see and validate this behavior for yourself. One of the pieces that I'm particularly excited about is graphics. I started my career in graphics. It has a special place in my heart, and XE2 is a lot of fun for me. This thing is bigger, it's faster, it has more AI, it has more raster, so I'll just jump right in. The first and foremost component is the vector, what we call the XE core, right? These are a combination vector engines and matrix math, aka floating point AI, and there's 8 of them in the device, okay? So those second-gen XE cores, that's what allows us to extract the 50% faster graphics performance, but it's the XMX or XE matrix extensions which allows us to extract the AI performance. That's where the 67 TOPS of AI comes from, okay? So the great thing about this architecture is its ability to just pull out way more raster performance than you were getting in the previous generation in about the same area with about the same core count, right? So the basic building blocks, you got the XE2 vector engine, which you might see shorthanded as XVE in life as we go on. Everything needs an acronym. And then bolted to that is an XMX array, right? And so once again, I just want to be very clear, 67 tops, that is based on int 8, okay? I know there's always some questions about how that number was calculated. That is an int 8 number, 67 tops, and that runs on XMX. One of the things that was driving this improvement, again, in the relentless pursuit of power, is that the graphics architecture in our Meteor Lake product did not scale all the way down to the lowest power envelopes. We needed two different configurations. There was the 28-watt Meteor Lake H config, more cores, more area, more compute. But then U-series Meteor Lake got a different configuration, smaller, because that larger graphics config just didn't go down to the low power we were looking for. And so now you can see XE2 with one configuration can cover that entire dynamic range of performance that we are looking for, right? So we've improved low power island, we've improved E-cores, we've improved the range of graphics, and you can see how this is starting to add up. The other near and dear place in my heart is display and media technologies. That's part and parcel of graphics. Love this stuff. I'll jump right in. VVC, we touched upon this very briefly, but you can call that H.266. It is the next generation video codec coming to market, and we support this right in our media engine for decode. Of course, AV1, encode decode returns from Meteor Lake, but we've also brought in embedded DisplayPort 1.5, DisplayPort 2.1, HDMI 2.1, and we can support 3 total displays. So the laptop display plus 2 more, or if the lid's closed, 3 external displays, so 3 pipes. VVC is a very interesting technology. It doesn't do a ton for file sizes. It reduces file size about 10%. H.265 is quite good in the file size category. But it also, and more importantly, introduces adaptive resolution streaming. So we've all had the situation where we're streaming a video over the web, and perhaps there's a hiccup in the bandwidth or a hiccup in the stream for one reason or another, and you get a pause. And then it resumes, and it's very pixelated. That happens all the time. VVC will eliminate the pause and pixelation because it can do real-time, on the fly, no change in streams, a resolution change or a bitrate change. You don't need to stop the stream and fire up another one anymore to change the stream that you're driving. It's kind of hard to see, but also screen content coding makes the text much, much better. This is a very simple task in theory, putting high contrast text on a black background, but modern video codecs are actually not very good at this. But VVC is awesome at this. So you can see kind of the before, which, you know, that word right there looks quite blurry. And this is at a relatively high bit rate. But on the left, you can continue to read the text. It's very legible. And then finally, 360-degree panoramic video, which would be especially interesting for HMDs, XR, AR applications for video. Embedded DisplayPort 1.5 is also a key innovation here. When I talked about platform power or total battery life being a function of relentless platform management, this is a key example. Displays have much more than just the panel going on. There's display controllers, there's lots of supporting and supplementary electronics, and that consumes power. But the reality of most productivity systems is that it's somebody staring at a relatively static screen. It is yours truly reading a Word document, or staring at the same PowerPoint slide for an hour a day, or reading an article on a web page, right? If you can just turn off the supporting or supplemental display technologies and let the panel refresh itself and turn the refresh rate down without flickering, you can save a ton of platform power. And so EDP 1.5 enhances this capability. And our demo showcase actually has live examples of panel self-refresh, so you can go check that out for yourself today. We also have adaptive sync built in to embedded DisplayPort 1.5, but the real thing that embedded DisplayPort does is it synchronizes the DisplayPort spec and the embedded DisplayPort spec, so they're now one common feature set. That was not always the case. Many of the features in DisplayPort are optional. They're not required components of the spec, and monitor vendors or display vendors can choose one option over another. Things like 8K, 4K, high refresh rate, adaptive sync, these are all optional, but different versions of DisplayPort had different sets of optional features, and that's somewhat burdensome to manage. So EDP and DP are now one and the same from an optional feature point of view. So the key thing I'd want to leave you with from a graphics point of view is in raster graphics, traditional 3D graphics, we are getting over 50% performance out of the engine, and that is on top of the 1.8 to 2x leap we gave you last year. So we're compounding on top of that. You get technologies like real-time ray tracing, AI upscaling, VVC, the latest display and media technologies, but most importantly, for all of the gamers in the room, this is a first-class citizen for driver development. This is the Battle Mage architecture. You will see that later in discrete graphics. And this will get the same gaming drivers, the same gaming features on the same release schedule that discrete graphics products do. And not every vendor does that. NPU is near and dear to my heart. My day job at Intel is AI. So we're now on our 4th generation NPU. We've started in that market under the Movidius brand. There were discrete neural processing units on add-on cards, and that took us through the first generation, first 2 generations. Meteor Lake was Gen 3. Now we're on Gen 4. The key takeaway is that we made this engine much, much wider. Right, last year, we had about a 12 TOPS accelerator, and now we have a 48 TOPS accelerator. And that comes from a couple areas. First and foremost, if we start down here, we got six neural compute engines now. You can think of these as cores if you want to, for simplicity's sake. But last year, we had 2. You can call them MAC arrays as well. You might hear Intel spokespeople call them MAC arrays. MAC arrays stands for multiply accumulate, which is just matrix math, AI math. So we had 2 MAC arrays last year, and now we've just copied and pasted. We've got more of them. Right? So that gives you the first big bump in performance. So if you go from 2 to 6, that's 3x. So how did you get the other 1x of that 4x improvement that we're talking about? That comes from the Shave DSPs. A DSP is a digital signal processor. It's a programmable coprocessor. And we use that to accelerate some of the functions that would otherwise require the MAC arrays to do. Okay? So that could be embedding or tokenization in an LLM, which is, hey, how significant is this word? When I say the word chip, am I talking about a microchip? Am I talking about a potato chip? Am I talking about a French fry? Right? AI doesn't know that intuitively until you tell it with technologies like embedding and tokenization, which helps AI understand the context clues. And every time you type a prompt into an LLM, you are doing some amount of embedding and tokenization. So this happens all the time. So offloading that to the Shave DSP and using that as a coprocessor is a key way we extract more. We also greatly increase the frequency of this engine. So that's another additional component. And then the last piece, DMA, stands for Direct Memory Access. Simple way of putting that is how much memory bandwidth does the NPU have access to? Okay? And with the increase in size of DMA, it can now access the full memory bandwidth of the system, the memory on package, which we know is LPDDR5X 8533 at the top end. This is really important, especially for LLMs. We touched on this in the morning keynote, but that first word you get back in an LLM is compute bound. That is just how fast is your engine. But every word after that depends on your memory performance. So giving the NPU full entitlement to all the memory bandwidth in the system allows the NPU to execute LLMs at full speed. We're talking 30, 35, 40 tokens per second with an LLM like Phi-3. It's extraordinarily fast. So we're very excited about this, but one of the things I want to leave you with is who is using these engines, okay? This is very, very important. We have contacts with over 100 different software developers with applications and features in flight. You may have heard Intel say we have 300 features coming to market through 2025, right? All those ISVs have clear plans about what model they want to use, some internal and proprietary to them, some publicly available, and they decide what engine is best for them. A company like Zoom, teleconferencing, their number one care about, battery life. Camera technology, teleconferencing, we've touched on that. That is a very intense task from a battery life point of view. So they're going to put NPU acceleration on their camera effects because that makes the most sense for what they care about. In fact, about 30 to 35% going into 2025, 30 to 35% of our software developers want to use the NPU, okay? So it's about a third of who we talk to. 40% will use graphics. So you've been wondering, perhaps, why do they have 67 tops on graphics and also 48 tops on NPU? Why not just all NPU? Well, it's because 40% of the software developers Intel is engaged with wants graphics. These are your content creation companies that have intense computational needs and want to do more. They want more generative AI. They want better object removal, better object detection, and they're going to use graphics to do that. Right? So it is not enough to just have a good NPU if you want to do AI well. And the other 30%, roughly, as we said, will go to CPU. So having all of these engines sets Intel up in a very healthy place based on what software developers want to do. And I'll sidebar on this for a moment. AI is an absolute tidal wave coming into this market. I understand many of you are skeptical about what AI will do. Why is it here? What's the point? In a couple years' time, we will absolutely reach a point where AI is infused in pretty much every piece of software that you are touching, whether you know it or not. Just like graphics, it's the same journey. They have the same kind of software stack, the same complexity of that software stack, the same care-abouts from the software developers. So getting this right, the engines right, the software right, is what puts Intel in a very healthy place 1, 2, 5 years out. We're not just thinking about what AI looks like in 2024 and 25. We are thinking about that multi-year journey until AI is literally everywhere. And I'm not talking just devices, I'm talking software, okay? It will come to games. It will come to office productivity. It will be in every piece of software that you use. So it's incredibly important to get this right. One of the key aspects of NPU4 for those developers who want to use the NPU is the massive boost in performance. So at the same power as last generation, we get about 2 times more performance, 2 times. But because of that additional, call it core count, or the additional MAC arrays, additional frequency, we just get so much more peak performance. So we went from 12 tops to 48, and we get 4x more performance. It's frequency, it's shaved DSPs, it's the increase in the size. Altogether, in the spirit of delivering a really great AI experience to the software developers who want this, as we touched on this morning, we're bringing over 120 platform tops, exactly 120 platform tops to market across CPU, GPU, and NPU. And again, I'll really stress this is what our software developers want us to do. It's that simple. There's a clear appetite from ISVs, and we are delivering the single best, the most balanced architecture for their needs. Connectivity has also been greatly enhanced. As you know from this morning, Thunderbolt 4 is integrated. One of the little details that doesn't always make it to a keynote is you are guaranteed a minimum of 2 Thunderbolt 4 ports on every Lunar Lake system that you touch. A maximum of 3 is possible, but you are going to get 2, okay? Wi-Fi 7 is now on chip, so you get, frankly, insane bandwidth, but also it has really great capabilities for multi-user, high intense usage scenarios. Wi-Fi 7 is a wonderful technology for managing congestion. It can even do like multi-radio. If you were in any way interested, I strongly recommend the connectivity session during the show. It's an absolutely fascinating look at how Wi-Fi 7 functions and what it can do for an office environment or a user who may be dealing with airtime congestion in Wi-Fi. We also have Intel Unison, Thunderbolt Direct Share, which allows you to just like drag and drop files or pictures or whatever you want between 2 systems because Thunderbolt is fast enough to give you a drag and drop experience. So integrating all of these cutting edge display, connectivity features, this is a foundational piece of what it means to be a great CPU. And these features too, they cost power, they cost area, they cost complexity. So being able to drive down our core power, our GPU power, our NPU power, frees up budget to do cool stuff like this, the state-of-the-art connectivity and display interfaces that you deal with on a regular basis all the time. One thing I did not touch on is that side memory cache. We did briefly hit that in the keynote this morning, but I want to touch on this. Memory transactions, going to memory, is electrically expensive. There's a high power cost to go to memory, right? So we've eliminated one source of that by moving memory onto the package, right? So you're not going off chip anymore. That saves, as we discussed, 40% of the power of running that memory by eliminating the PHYs. But the other thing that we've done, the other neat trick is there's an 8 meg cache on the SoC that services multiple engines. You may not even need to go to memory at all if the data fits in that cache. So NPU can use that, GPU can use that, core clusters can use that. That is a kind of a universal, omnipresent 8 megabyte cache that further reduces SoC power, which further reduces platform power. And this is another demonstration of the fact that it's not x86 versus ARM, it's how you build the chip, how you lay it out, okay? So if I were to briefly summarize, Lunar Lake, power was our #1 focus, driving transformational energy consumption, something that you have never seen before in x86, I promise you that, is what this chip will do. It's through a combination of more efficient graphics, more efficient E-cores, more efficient thread scheduling, more efficient packaging, more efficient platform management. Every single piece of this chip was touched for power management. And you do not always get that in CPU design. Sometimes you get a bump in graphics, but CPU cores are relatively flat year over year, or you get a bump in AI, but maybe you don't get graphics. Everything was improved gen on gen in Lunar Lake. And it's products like this that brought me to Intel. I believe this will be the single best ultra-thin PC processor come holiday this year. It's the processor that I want on my desk at home. It's the processor that I want in my backpack because from a technological, architectural perspective, it has everything that I am looking for. It has the graphics chops to, I just got back into EverQuest. I don't know, any EverQuest fans are out there? Yeah, all right. I just got back into EQ, so my life is shot again. And I want to be able to play a game like that, something modest on a laptop that I can chuck into my backpack for under 3 pounds. That's what this chip can do. It has great power management, great battery life, and you will see that when these systems hit the market. So a couple of cleanup comments that I want to make that weren't, maybe we're not touched on. I know we're using TSMC, but this is assembly and packaged at Intel. The design by Intel, the architecture by Intel. And that is how we are extracting the power that we're extracting and the features that we're delivering to you.